Hello students, welcome to the course Network Theory. In the previous video, we solved few problems on network Norton's theorem. So they are of the first of its kind. So there are only independent sources and resistors. So straight away we have used the first case. Okay. So in this video, we look at the remaining cases. So now second case is along with independent sources and resistor, if there is a dependent source. Okay. So how we solve the problem. Okay, so note down the question. Find the value of IB using Norton's equivalent circuit for the circuit shown in figure. Take load resistance RL is equal to 667 ohm. Okay, so this is the circuit they have given. So it is a 12 volt, 6000 ohm. It is 2000 IA, 1000 ohm, and here the current IA is shown, which is the controlling variable of this dependent current source, voltage source. And this is the load resistance RL, okay, which value is 667. We need to find the current IB in this. Okay, so current IA flows in this branch, IB flows in this branch, so we have to find the IB using Norton's theorem. Okay, so for that what we have to do as a first step, so we need to find the Norton's current. For that we'll remove this load. For the first case we'll connect a current ISC. Okay, so that is the short circuited current we will show, and we'll find the ISC. Okay, so that is the idea. First note down this question. Okay, okay, we'll solve this. As I said, to find IB we need to remove the RL from the circuit first, and the resulting circuit is shown here. Okay, so this is a removed. Okay, earlier it was connected, this is removed now. So only X and Y terminals are there. Okay, so 6000 ohm, 2000 IA, 1000 ohm IA, and 12 volt. Okay, remaining circuit as it is, just we have shown the removed part of the things. Okay, so next step is we need to short these terminals X and Y, and you have to show the current ISC, short circuit current ISC, that is shown in the next figure. Okay, so you pause the video and note down. So the first step is to find IN, okay, or ISC. So we'll short the terminals XY and show an ISC now. So we need to solve now. Okay, so just looking at this, so as previously I told you, resistor in parallel with a short circuit, nothing but this branch does not have any current. Okay, because the resistor value is 0 according to current division rule. So this branch there is no resistance, multiplied by resistance is 0 means what? Current is 0. Okay, so that's why, so this is 0. That's why IA value is 0 by 1000 amps equal to 0 amps. So because of this 0 amps, so this circuit is a short circuit. Okay, 2000 into 0 means 2000. So this becomes a short circuit. What is remaining here? 12 volt in series with 6000 ohm. Okay, okay, what is this current? So it is a Ohm's law, V by R. Okay, I equal to V by R. So 12 by 6000. So straight away written, it is 2 milliamps. Okay, use the calculator. You got IS equal to 2 milliamps. Hope you understood this. Okay, and the second part now, that is Rn. Okay, so now there is a dependent source here. We could not do deactivate the source. We could not do. So we have to go for this ratio of VOC by ISC. That means as we have done in Thevenin's equivalent circuit, we have to find now open circuit voltage. The ISC whichever is shorted earlier, we remove that short and we will make it open, and we need to find this open circuit voltage or the terminal voltage XY, or it is also called as Thevenin's voltage VTH. Okay, so to find this voltage here, what we require here is across this resistance, what is the current we require. If you multiply the resistance value with that current, we will get the VTH. For that we don't know the this branch current. In this case there is no short here now. Okay, earlier it was told 0, now it is not 0, it is having a value. So what we'll do, we'll apply a KVL to this loop. Okay, so when you apply this KVL, what will happen? So both way you can do. If you are considering minus plus, okay, so normally I will use plus. Okay, you can use whichever comes the first, that also you can use minus 12. So normally current enters through resistor terminal, that's why it is plus minus. Here also plus minus. Okay, so it's because of this plus, so it will be 6000, and the current is IA. Okay, in this branch total current is IA only, so that's why same thing I will consider. Then you have plus minus voltage source of value 2000 IA, so that's why it is plus 2000 IA. So how you write the KVL, and then again plus minus is there, it is 1000. Okay, so 1000 IA equal to 0. This is the KVL equation. So if you add this, so what will happen? So 6 plus 2 8 plus 1 9000 IA equal to 12. 12 if I take right side, it will become plus 12. So then IA is equal to 9000, sorry, 12 by 9000. Okay, that we will do in next step. So hope you have understood KVL. Okay, so that is what written here. Okay, in the another manner. Okay, minus to plus as plus and plus to minus as minus. Voltage rise 12, voltage drop 6000 IA, 2000 IA, 1000. Same answer you will get, 9000 IA equal to 12. I is equal to 12 by 9000, which is 4 by 3 milliamps. Okay, so VOC or VXY is equal to now 1000 IA. So just multiply 1000 into 4 by 3 milliamps. So milli and 1000 cancel out. So you'll get 4 by 3 volt. Okay, which is approximately 1.333 something. Okay, we'll keep as it is. What we need to find here is the Rn. Rn is nothing but the ratio VOC by ISC. VOC is 1 by 3 and this is 4 by 3 and ISC is 2 milliamps. Okay, so that is written. So when you take that, take this ratio, you will get 667 ohm. Okay, so that is the answer. So now just write the Norton's equivalent circuit. So there is a 2 milliamp current source along with 667 ohm resistor. Okay, so this is the Norton's equivalent circuit. Simple. Okay, so this is the Norton's. So question is not over yet. They have told the current IB. So here the current IA is there. So IB current we need to find by connecting the circuit B, that is the 667 ohm load resistance. Okay, note down this. I will go further. Reconnect RL equal to 667 ohm between the terminals XY. Okay, so which is shown as it is. So now this is a current division rule. There is a total current 2 milliamps is flowing here, and it is a same resistance. Both are having same resistance value of 667 ohm. So when you have such cases, if you write the parallel case here, both resistance are equal means what? R into R by R plus R, which is 2R, right? So one R will cancel out. So what is the answer you will get always? So this you can remember as a formula. If two resistances are connected in parallel, equal resistances, then their resistances will divide. If there are two resistances are in series, they are adding up. Okay, they are equivalent to multiplying by 2 times. Okay, so here it is parallel, so that's why divided by 2. That means 667 divided by 2, like that. Okay, but what we want here is the current. So current division rule I'm applying. 2 into 10 to the power minus 3. Opposite branch is 667 divided by 60 plus 667. Okay, which is 2 into 667. So 667 cancel out. 2 by 2 is 1. So milli is as it is. So you got IB equal to 1 milliamps. Okay, so finding equivalent resistance also you can do, but here it is different current, right? So even if you do that way, you will get something this value. Okay, so current division rule. Okay, you can note down what is the rule we have used to find out this. Okay, current division rule, it is 1 milliamp. That means current will divide here when two parallel resistance equal current. No, so 2 milliamp is equally divided as 1 milliamp and 1 milliamp. If it is objective type, straight away you can write, but it is a numerical type, so you need to explain the steps. That's why current division rule is shown here, and this is the steps written. Clear? Okay, so this is just an additional I have told you. Fine, so we will take the third case now. There is no independent source at all, only dependent source and a resistor combination. So how you solve the Norton's equivalent circuit? Okay, as we have done in Thevenin's. Note down the question. Find the Norton's equivalent for the circuit shown in figure. Okay, so 100 ohm, 50 ohm, 200 ohm, and you have a 0.1 V1, which is a dependent current source. Okay, so voltage dependent, voltage controlled current source it is. Okay, so V1 is across 100 ohm, and this is the terminals opened, it is shown. Okay, so since there is no independent sources, so what is the step we have to follow? Either you have to connect a current source of 1 amp and you have to measure the voltage across this as VAB, or you have to connect a 1 volt voltage source and you have to measure the current IBA. and you have to take the ratio. Okay, so for the sake here we will connect a 1 amp current source now, and we will apply the node analysis, and we will find the voltage here VAB, which is across this 100 ohm. Okay, note down this question. Okay, since there are no independent sources present in the network, so our Norton's current or ISC is equal to 0, which means it is a open circuit. Okay, you don't have the current source part at all. But to find Rn, we inject a current of 1 amp between the terminals AB. This is as shown. Okay, so this is what I have done. Okay, so these are the terminals AB. I have connected a 1 amp current source upward direction, called as voltage across, that is called as VAB, which is equivalent to V1. Okay, so for applying node analysis, I call this as V1 and this as V2, and I'm applying the KCL or node analysis here. I'm not interested in V2 voltage here, but I'm interested in V1 because which is equivalent to VAB. Okay, so that's why to solve with equations we require both the equations, right? That's why I have taken V2. Okay, so we'll apply the KCL here. So if you apply the KCL at node 1, okay, so what you have here is 1 amp current is entering the node, which is opposite to the our assumption, right? So in node analysis we will consider currents are leaving the node. Okay, accordingly we will take, so this is opposite to the convention, so it is -1 is written. Okay, plus VA, this is the reference node, so VA minus 0 means V1 by 100. Okay, so this is V1 by 100 plus, then with respect to these two node you have 50 ohm, so V1 minus V2 by 50, that is the current across the 50 ohm. V1 minus V2 by 50 equal to 0. Okay, this is the first equation. Actually I have written straight away. Okay, so V1 by 100 plus V1 minus V2 by 50, I have taken one right side, it becomes plus. So now we will just take the group the V1 terms, V1 by 100 and V1 by 50. Okay, and take that ratio in calculator, it will come 0.03 V1, and then minus 1 by 50 V2, which is minus 0.02 V2 will come equal to 1. Make it as equation number 1. Using calculator we will solve that. Similarly, we find the equation for second V2. What you will get? So I maybe made mistakes over there, so just note down here only. So V2 by, so all the currents are leaving. Okay, again the same assumption, there are 3 branches are there. With respect to V1 now, so V2 minus V1 will come now, divided by 50 plus downward direction you have 200 ohm, which is V2 by 200. Note down this equation, I maybe made mistakes. Okay, not mistake, overwriting I have done, plus, so this current leaving the node, okay, which is in the direction of the convention, that's why it is plus point V1 equal to 0. Okay, so now simplify this. V1 you have minus 1 by 50. Okay, here only you do minus 1 by 50 plus 0.1. Okay, so group this 0.1 V1, take the LCM and solve that, or take the calculator and do it. And then V2 you have 1 by 50 and 1 by 200. Okay, so use the calculator, take the ratio 1 by 50 plus 1 by 200. Okay, equal to into V2 equal to 0. Okay, I have taken in different manner, maybe it may be confusing. This is understood to you. Okay, so this equation you write, and then you use the calculator for V1 part and V2 part, same like fraction part you will get. Okay, so note down that, pause the video and note down. So this is what, okay, so this is here overwritten, that's why confusing maybe, don't write. So write the previous step what I have shown. So take the ratio here as you got same 0.08 V1 plus 0.025 V2 equal to 0. This is the equation 2. Now use the calculator in equation mode for two unknowns. Okay, A1 B1 C1, A2 B2 C2, you enter and you solve that, you will get two values X and Y, but you require only V1. Okay, that's why I have noted. V2 also will come some value, but I have not noted down because I am interested in V1, which is a VAB voltage. Okay, 10.64 volt I got, which is equal to VAB written here. See, now if you take the ratio for Norton's equivalent resistance, okay, VAB by 1 amp is the current source we have connected. No, that's why it is 10.64 ohm. So now just Norton equivalent circuit you will have. Okay, even you can show this or you can show the current source also. Okay, this is the current source in parallel with resistance in Norton's, but current source is 0 amps. So like that also you can show with a symbol 0 amps you can show, which is nothing but a open circuit equivalent to single resistance. Hope it is clear. Okay, so we have considered both the cases now. Now we'll take one more case, that is we'll club the Thevenin's theorem and Norton's theorem now. Okay, as we have told, from Thevenin's theorem we can find the Norton's theorem equivalent circuit. Okay, so we'll consider one problem, we'll solve using Norton's Thevenin's equivalent circuit, and then we'll do the source transformation, it will become Norton's equivalent circuit. Okay, so such kind of one problem we will see. With that we may be ending the Norton's theorem part. Okay, so note down the question. Find the Thevenin's and Norton's equivalent circuit for the circuit shown in figure. Okay, so note down this figure. So you have 50 ohm, 50 volt in series with 2 ohm, 4 ohm in parallel with 5 amps, then 10 IA dependent. What is this? Voltage source. Okay, current controlled voltage source you have, and this is the terminals AB. So they told to find out both Thevenin's as well as Norton's from single circuit. Okay, so no need to follow the separate step. If you got Norton's, convert it into Thevenin's, or if you are familiar with Thevenin's, convert it into Norton's. Anyone you can do. Fine. Okay, so what is the first step we can do here is current source in parallel with resistor is there. It may be difficult for you to find out here VAB, right? So for that what you will do, so you convert this into a voltage source in series resistance. Source transformation you apply and make the circuit 5 into 4, which is 20 volt in series with 4 ohm. Okay, so like that you make a circuit and then you can easily go for the next step. Okay, that is the first step I am applying here. Hope you have noted down. To find VTH, so performing source transformation on the 5 amp current source, we get the circuit shown. So this is shown here. Okay, so the current direction is downwards, that's why it is minus plus. Okay, conventionally current flows from minus to plus, that's why it is minus plus 20 volt is taken. Okay, 4 ohm 10 IA remaining as it is. So now we have to find the VTH. Okay, so VTH means what? This loop voltage. So in this loop what you have? 20 volt you have, 4 ohm you have, 10 IA you have. Okay, but we don't know the branch current. This branch current we don't know, which is IA, and here also IA is dependent on this current. So that's why IA we require. That's why first we'll apply the KVL to this branch, this loop. Okay, so when you apply the KVL to this loop, what you will have? Minus to plus, plus I have written 50, and current drop always through the resistor, plus minus, right? So it is minus 2 IA, then minus to plus is there, that's why plus 20, then plus to minus is there, minus 4 IA equal to 0. Even if you are applying according to the sign first, so it will be minus 50 plus 2 IA minus 20 plus 4 IA, which is same as this. Okay, interchanging the signs. Okay, so whichever convention you can follow. So now simplify this. You have minus 4 minus 2 minus 6 IA plus 70 equal to 0. If you take the minus that side, it will become plus 6 IA equal to 70. So from this, what is IA equal to? 70 by 6, which is 11.667 amps. Just you can observe. Okay, so you got the IA now. Now you can apply the KVL to this branch, so you'll get the VTH. Okay, so what is this branch now? KVL you can write here, minus to plus is there, which is anyhow you can write. Okay, so minus 4 IA opposite to the branch current, no, minus 4 IA, then plus or minus is there, plus 20, here plus minus is there, plus 10 IA, and this is plus minus, so plus VTH equal to 0. This is the KVL applied to this loop. What you have to do is IA you know 11.667 amps, that you need to substitute here. Okay, and take it all the value, add it and take it to the right side, it will become the VTH equal to answer. Okay, so it may be negative answer, don't worry. Okay, applying KVL around the right mesh. So since I don't have the figure here, that's why I explained there only minus 20. Anyhow you can, anywhere you can start. Okay, I started from this source, that's why it came first. Okay, minus 20 minus 10 ia minus vth plus 4 ia is equal to 0. Reverse I have taken, minus 2 plus s plus I have taken. Okay, so vth equal to vth I have taken right side, remaining left as it is minus 10, here plus 4 ia and minus 10 ia I have minus 6 ia. So then ia I will substitute 70 by 6, which is equivalent to 11.6, right? This I have substituted because 6 easily cancel out. So minus 20 minus 70 equal to minus 90 volt. Okay, so this is the VTH. So what is the meaning of minus 90 here? Means when you are writing a equivalent circuit, you have to write normally plus minus, we will write normal convention. Now you have to reverse it, minus plus you have to write, and plus 90 you can write outside. 90 volt with sign changes, or you can write same sign with minus 90 also you can write. Okay, both convention you can follow. So this is the VTH part. Now to find the RTH part, Thevenin's equivalent resistance, we have to go through the second case. That is, here along with independent source, we have a dependent source here. That's why we need to short the terminals and we have to find the ISC current. Okay. To find RTH, we have the ratio open circuit voltage by short circuit current. So to find the short circuit current now, we have to short the terminals AB. So the same circuit, we have to short the terminals now, and we need to find the current ISC now. Okay, so how to do this? You can go for loop analysis as well as node analysis, whichever way you can do this. Note down this figure. So I have applied the KVL, so I will get two equations now. Okay, so you have the circuit there, just look at. So what I have here is confusion as there. Okay, so my whichever way you can do, as I told you. So minus 2 plus 50 I have taken, then current through resistor minus 2 ia, then minus plus is there, right? So it is a rise plus 20. And now current is not open, right? Circuit is not open. If circuit is open, current is 0. That's why ia used to take earlier. Now since current is there, so we have to consider ia minus isc. Okay, which is equal, this is the only change compared to the first KVL. So simplify this now, minus 2 ia minus 4 ia, it is 6 ia. You have taken right side, and then minus 4 minus isc plus isc. Okay, so if I take right side, it will become minus 4 isc is equal to this 50 and 20 are added here. They are in the same place, 70. Make it as equation 1. Okay, so you can write one more step if you are confusing. Okay, I familiar with solving many meshes, I will write directly. Okay, even you are familiar, you can do this. Okay, but in case if you write, so require one step, you do that. Okay, so what you do, 50 plus 20 70 minus 6 ia plus 4 isc is equal to 0. So then you take the current separately and this one separately, then you will get 6 ia minus 4 isc is equal to 70. Okay, applying KVL around right mesh. Okay, right side you have again 4 elements. So current minus 4 isc minus ia. Okay, so now with respect to isc will take positive and that, and this the notation, there you have plus minus. Okay, so that's why it is taken minus 4 isc ia, then you have plus minus, that's why minus 20, and then minus 10 ia. Okay, so plus minus we have taken opposite manner, all equal to 0. So all in the plus minus plus minus plus minus is there, right? So now simplify this same way. Okay, you make two equations. So here minus 4 isc plus 4 ia minus 20 minus 10 ia equal to 0. You can write one more steps. Then ia you write first because same pattern. Minus 6 ia you will get plus 4 ia minus 10 ia minus 6 ia, and this minus 4 isc and this 20 taken right side, it will become 20. Make it as equation 2. So again we are interested in the second current now. Okay, not in ia current. So again you go through the complex equation mode, two unknowns, enter a1 b1 c1 a2 b2 c2, and you will get two answers x and y. So note down the y answer, which is equal to isc. Second part, no, x it will come, you can note down, but it is not used in problem. Only second part isc we are interested. So note down that y value, which is minus 11.25 amps. Okay, So here current you got minus, that means you have to current direction. Conventionally we'll show current direction as upward. Now we have to show the current direction downward. Okay, nothing but if you show upward you have to write minus 11.25. If you show downward you can show plus 11.25. Okay, so both are equivalent. Okay, these are some of the properties of the voltage sources. Okay, so now RTH is the ratio of this open circuit voltage you got minus 90 and this is minus 11.25. So when you take the ratio you'll get 8 ohm as the answer. Okay, so hope it is clear. So now finally we have to write the equivalent circuit. Okay, you got the VTH and RTH now. So VTH is C here. Okay, so this is what I told you. So conventionally the thing, sorry. So conventionally it will be voltage source in this manner, right? Plus minus, and it is in series with the resistor in all the Thevenin equivalent circuits seen so far. Now because of the minus value, if you want to write plus 90 volt outside here, then you have to just change the polarity. Okay, what I have done, minus plus I have written, and like that I have written. So that's why don't confuse this minus part and this is plus part. If you want to write same way, plus minus sir I will confuse, then write no issues. Okay, outside you write minus 90 volt, so it is also no issues. Okay, and this is 8 ohm resistance. Okay, so these are the terminals AB. So this is the Thevenin equivalent circuit first part. Now to do the Norton's equivalent circuit, no need to go back again. Okay, so just do the source transformation on Thevenin equivalent circuit. So you'll get the IN and RN. IN is VTH by RTH by formula. So minus 90 by 8 you got 11.25 amps. Even you have got the short circuit current which is equivalent to IN, right? So and RTH is equivalent to RN from the derivation only we know, right? So just you write, so current downwards and outside we have written plus. If you want to write upward only again, as you are, I want to write sir I will confuse, I will follow one single convention, you can do that. Okay, you show upwards, this is 8 ohm, does not change. Here you can write outside minus 11.25 amps. Okay, but if you want to write outside plus, just reverse the direction of the current, it will be equivalent. Okay, fine. So with this we have solved all the varieties of problems in Norton's theorem. Okay, so with this we are completing the 4 theorems in this part. Okay, so left out with only one theorem, that is maximum power transfer theorem. So that will take up in the next video. Okay, so hope it is clear. So 3 problems I have solved in this video. Okay, one is based on dependent sources, another on only dependent sources, and third one we have used both Thevenin's and Norton's equivalent circuit. Okay, so with this I will end the session here. In the next video I will start with the new theorem. Okay, thank you.